Hello everyone. In this video, we will talk about the joint probability function that describes the probability of two or more random variables happening at the same time. In the previous videos, we talked about the single random variable and we covered the topics like probability mass function, probability density function, and the distribution function for a single random variable. In this video, we will cover topics like joint probability function and joint distribution function. And we will cover both the continuous and discrete cases. Let's first start with the discrete case. Let's say x and y be two discrete random variables, then the joint probability function of x and y is given by this expression. In other words, we can say that we are interested in knowing the probability that x takes the value x and y takes the value y. Now, there are two conditions that this joint probability function must satisfy. Number one, the value of this function for all values of x and y must be greater than or equal to 0. And the number two condition is that the value of this function when summed over all values of x and y must be equal to 1. So these are the two conditions that this joint probability function or the joint probability mass function should satisfy. Let's look at an example. Imagine rolling two dice, one red and one blue. Let's say x is the outcome of red die and y is the outcome of blue die. Now each die has equally likely outcomes that are numbers from 1 to 6. And we are interested in finding the probability that x is equal to 3 and y is equal to 6. Since x and y are both independent events, that is for all values of x and y, and we know from the definition of independent events that knowing one does not give any information about the other. So in that case, the joint probability of x and y is equal to the product of probability of x and the probability of y. And the probability of x or the probability of y, we have solved this kind of example in the previous videos, which is just rolling a single die. Now we have 6 outcomes that are equally likely, so the probability of x or probability of y will be 1 by 6. Now if we multiply, we get to the answer for all values of x and y. The joint probability is 1 by 36. And since it is true for all values of x and y, we can say that we find the answer that the probability that x is equal to 3 and y is equal to 6 is also 1 by 36. So this is how you are going to solve the joint probability function problem for a discrete case. Now there is another easier way to look at the joint probability functions, and that is through joint probability tables. So here we have two random variables x and y, and these are the possible values that these random variables can take or allow. And in the middle we have the joint probability values, and on the margins we have the marginal probability values. If we sum all the joint probability values, the result should be equal to 1. And the same is true if we add the marginal probabilities for either x or y, the answer should be 1. And that is the total probability. Let's look at an example. In this case, suppose a survey asks students about whether they study regularly, so that's the random variable x, and there are two answers to it, yes or no, and whether they pass the exam, and that's the random variable y, and again the answers are pass or fail. So we collect some data, so that is the survey data, and then we created a joint probability table which we saw in the previous slide. So in this case, this is how the joint probability table will look like, And again, in the middle, we have the joint probability values. And if we sum these values, we can see or confirm that these add to 1. That is the condition number 2, the joint probability function must satisfy. Now, what we want to do here, we want to calculate these marginal probabilities, and that's what we will see in this slide, how to calculate and populate these marginal probabilities and fill this table. So let's start with row number 1 when x is equal to study and calculate the marginal probability. So in this case, we will simply add the probabilities in the first row. So 0.4 plus 0.1 is equal to 0.5, and we will do the same for the second row, and we can see that we are adding zero point 0.2 plus 0.3. Again, we end up with 0.5, and as we can see that if we sum these two numbers, we end up getting a number that is equal to 1. Now let's calculate the marginal probabilities for y, and when it's equal to pass, we can see that we are summing 0.4 and 0.2 and we get 0.6, and then for fail we are summing 0.1 and 0.3 and we are getting 0.4. Again, if we add 0.4 to 0.6, we end up getting a result that is equal to 1. So that is all about marginal probabilities. One interesting observation that you must have seen in this is that the marginal probabilities are probabilities that we get regardless of the other variable. So we ignore the other variable. For example, when we were looking at x is equal to study, so it was regardless of pass and fail, we want to understand what's the probability of x is equal to study. And that is what marginal probabilities are about. Okay, so let's move on to the next slide. And in the next slide, we want to differentiate or understand the difference between marginal and conditional probabilities. So they both are different because marginal probability function, as we have seen in the previous slide, describes the probability of one variable ignoring the other. So we are not concerned about the other variable, whether that other variable or the event has occurred or not. So we are only interested in getting the probability of one variable. So we were interested in finding the probability of study regardless of passing or failing the exam. Now, on the other hand, the conditional probability function describes the probability of one variable given that the other has happened. So that is different. So now we are concerned that one variable has already happened and how is the probability of the other variable going to be affected by that event. So that is the conditional probability. Now this the multiplication rule that actually explains the joint probability distribution, and it relates to the conditional probability and the marginal probability. And we can see the conditional probability, that probability of x given that y has occurred, times the probability of y, which is the marginal probability in this case. So now let's try to solve another example and improve our understanding. So we have an example in which we want to find the probability that a student studied given that they have passed the exam. So this is the same example, the same numbers that we have seen in the previous slide. Now we have changed the question. So now we are interested in finding in the conditional probability instead of the marginal or the joint probability functions, probability values. So now we can use the multiplication rule. So we can use the multiplication rule and we could see that the probability of x is equal to study given that y is equal to pass, that event has already occurred. So can be obtained through the um, joint distribution function or joint probability of x and y. divided by the marginal probability of y. And if we extract the numbers from the previous slide, we get zero point 0.4 divided by zero point 0.6, which is equal to 2 by 3, or 67% probability that the student studied and they passed the exam. Okay, so now let's see what the joint probability function looks like for the continuous case. Again, a reminder that the joint probability function describes the probability of two or more random variables happening at the same time. So in the continuous case, the definition looks like this. Let's say we have x and y, and these are two continuous random variables. Then the function f is the joint probability or the joint probability density function of x and y if it satisfies these conditions. The condition is that value of x must be greater than or equal to 0 for all x and y. Again, Number two is the same like we've seen in the discrete case, but here, since we are dealing with the continuous case, so the summation gets replaced with the integrals, and now the integration over all values of x and y must be equal to 1. And the third property or the third condition is that the probability that the x and y belongs to a region R must be equal to the integration over that surface, so for all values of x and y. So we are basically interested in finding the total volume bounded by this surface. So that is the definition of joint probability function for a continuous case. And now let's look at the distribution function. So before we do that, let's review this point. So joint probability mass function gives the probability at a point. So this is very important to understand and differentiate, whereas joint probability density function is not a probability but an intensity, because the probability comes from integration over an area. So we integrate over an area, and that gives us the probability. Let's now see the distribution function, and the definition for the distribution function for two random variables x and y is like this. And the only difference between these two discrete and continuous case is again the replacement between uh, summation and the integration. For the discrete case is the summation, and for the continuous case is the integration. That's how a joint cumulative distribution function is defined. It gives the cumulative probability up to a point x and y, and instead of asking about the probability at a point, we are basically asking about the probability of being in a region. So that was all about joint distribution function. So in this video, we have covered the joint probability functions and the distribution functions. We have looked at different examples through joint probability tables that makes visualizing the joint probabilities, the marginal probabilities, and understanding these concepts easier. So that's all about today's video, and we'll be back in the next videos with more problems, and we'll continue from this point. So please keep watching, and see you all in the next video.